Viral Genomics and Bioinformatics. From the recognition by Ivanovsky in 1892 that tobacco mosaic disease is caused and transmitted by fine pore filtrates, viruses have been isolated, characterized, identified and studied from animals, plants, protists, bacteria and even other viruses. As human and global public health pathogens that can be highly contagious and have devastating morbidity and mortality consequences, viruses are the focus of much research. The difficult challenge has been to define and study a minuscule being with the appropriate tools. In the past, these tools often provided only low resolution views. A first approach to studying an unknown virus is to know exactly its identity and to place it into context of other related and non-related viruses. For human and public health, this is important as the identity may provide a course of action to limit the effects of the pathogen. Although in general, large data sets of related viral genomes from a family are just being assembled, there are available sets of genomes from members of certain virus families that are of recent and critical interest in the context of human and public health issues. Many of these data sets have either been recently assembled and reported, such as rhinovirus, or have been reviewed recently, for example, rhabdoviruses, papillomavirus and human immunodeficiency virus or HIV. Rather than attempting to provide a comprehensive survey of many virus families with multiple genomes sequenced and analyzed, a goal of this special issue is to provide a sampling and a range of the virus families that have been and are of importance such that multiple genomes have been sequenced and analyzed using bioinformatics methods. From these contributions, one will see that genomics and bioinformatics are intertwined. At one end of the spectrum are human adenovirus, which contain DNA genomes of 35 kb. Once considered large genome viruses, these are provided in contrast to the much larger genomes found amongst the Iridoviridae with DNA genomes of 106 kb. Eaton et al. Reviews these. In addition, Hendrickson et al. Examines the Poxviridae genomes, which range from 130 to 375 kb. For comparison, Wu et al. Reports on the coronaviruses with the largest genomes found for RNA viruses, that is 26 to 38 kb. This report on coronavirus illustrates the importance of viral genomes and bioinformatics in monitoring and identifying global pathogens rapidly and effectively, allowing for measures to be taken. The NCBI database provides a comprehensive list of 6021 viral genomes, their features, accession number, host and the taxonomic details. Genomics of bacteria and archaea. The first bacterial genome was sequenced in 1995 and the first archaeal genome in 1996. Soon after these breakthroughs, an exponential rate of genome sequencing was established, with a doubling time of approximately 20 months for bacteria and approximately 34 months for archaea. Comparative analysis of the hundreds of sequenced bacterial and dozens of archaeal genomes leads to several generalizations on the principles of genome organization and evolution. A crucial finding that enables functional characterization of the sequenced genomes and evolutionary reconstruction is that the majority of archaeal and bacterial genes have conserved orthologs in other, often distant organisms. This is a screenshot of UCSC Archaea genome browser. Despite the tremendous variety of lifestyles as well as metabolic and genomic complexity, bacterial and archaeal genomes show easily discernible common architectural principles. The sequenced bacterial genomes spans 2 orders of magnitude in size from 180 kb in the intracellular symbiont Carsonella rudi to 13 mb in the soil bacterium Sorangium cellulosum. Remarkably, bacteria show a clear-cut bimodal distribution of genome sizes, with the highest at 2 mb and the second smaller one at 5 mb. Although there are many genomes, of intermediate size, this distribution suggests the existence of two more or less distinct classes of bacteria. The possibility remains that the bimodality of the bacterial genome size distribution is due to the bias of the genome sequencing efforts towards smaller genomes, such as those of symbionts and parasites. But with the growth of the genome collection, this explanation is becoming increasingly less plausible. Archaea are less diverse in genome size, from around 0.5 MB in the parasite Nanoarchaeum equitans to approximately 5.5 MB in Methanosarcina barkeri, and show a sharp peak at approximately 2 MB that almost precisely coincides with the position of the highest bacterial peak, and a heavy tail corresponds to larger genomes. As the representation of archaeal genomes in the current database is much less complete than the representation of bacterial genomes, it remains to be seen whether the genome size distributions in archaea and bacteria are genuinely different, or the differences only reflect sequencing biases. That is, a second peak might appear in the archaeal distribution once additional larger genomes of mesophilic archaea are sequenced. All very small, approximately 1 MB, with a current record belonging to the abundant marine, a proteobacterium Pelagibacter ubique SAR 11 at 1.3 MB. Notably, with the progress in genomics, it has become clear that there is no gulf in the genome sizes between bacteria and archaea, viruses and eukaryotes.